Good afternoon and good morning, everybody. Welcome to this EDITS webinar on new avenues for macroeconomic modeling. My name is Stefan Pauliuk. I work in industrial ecology, the field that studies the material and energy flows related to industry and sustainable development. And I'm part of the EDITS network, which we first would like to introduce to you in case you are not familiar with our team and our network yet. EDITS stands for Energy Demand Changes Induced by Technological and Societal Innovations. And the idea is to systematically study so-called demand-side solution, achieving high levels of well-being with less energy use, material use, and maybe also economic output. And it's a project funded by Japanese institutes, especially the RITA Institute, and the Ministry of Economics, Trade and Industry in Japan, and hosted at IASA, International Institute for Applied Systems Analysis in Luxembourg, Vienna. And our objective is to create a research community that focuses on demand-side solution with improved modeling, improved data, and improved interdisciplinary science to also be more policy relevant in our recommendations on the future trajectories of supply and demand, and of course also of industrial production. The seminar today is organized as a Zoom webinar. That means we see all of you and you can then raise your hand during the discussion sections. We'll explain in a minute how this works, and then we can sort of say, put the spot on you and activate your camera and microphone. This will be possible. So either by raising your hand, you can indicate that you want to later contribute to the discussion, or you can use the Q&A button, which we'll then see in the chat. The EDITS project has a number of working groups. One of them deals with industry. And here our colleague Dominic Wiedenhofer and I and a large team of about 20 scholars coordinate a large reviewing activities of industrial modeling of how industry needs to transform or should transform under future scenarios, especially also low demand scenarios. And here we came across a new family of macroeconomic models that adds new feature to compare to how economic modeling was done so far. That includes energy flows, that includes also different demand trajectories to study how industry needs to transform towards a sustainable future. And then I, a few months ago, reached out to our colleagues, Paul Brockway, Jaime Vega, and Carey King, who are with us today. And they all, within 2 days, accepted to present their recent work, which we included in our review here today in this webinar. So thank you so much for that. And we will have these 3 presentations by Paul, by Carey, and by Jaime. And each of them will be about 15 minutes long, followed by a rather short Q&A session, usually clarification question, so that this first part of the webinar will be about 1 hour, last for 1 hour. And then we'll have a more in-depth discussion on the overall modeling approach for sustainable industry futures. And after this introduction, I would now like to introduce our first speaker. This is Dr. Paul Brockway from the Faculty of Environment at the University of Leeds in the UK. Paul is an associate professor at this faculty in energy and economics at the Sustainability Research Institute and holds a 5-year research fellowship on applying thermodynamic laws to the energy GDP decoupling problems. So that includes exergy economics and studying how thermodynamic laws and energy conversion actually impacts industrial activities at the large scale. Paul, with that, we are ready to start, and I will stop sharing my screen so you can take over. The floor is yours.
Thanks very much. Okay, let me share my screen. And let's see if this works. First hurdle. Okay, hopefully you can see my screen okay. Yeah, okay, thanks very much. Yeah, so I'm one of the first of our 3 speakers, and I'm going to take you through a little bit of the background to our Marco modeling framework. So it's a macro-econometric resource consumption model, which has been built over the last 5-6 years, and has spun out of the work that our broader exergy economics community has built. So I'm going to, I guess in my time today, we're going to split it into 4 parts and address 3 weaknesses, I guess, in mainstream models that are addressed by Marco, or let's call them 3 strengths, I guess, that feature in Marco. And so these topics are going to be final to useful energy conversion, so thermodynamic conversion of energy into useful work. The second part is energy's role in economic growth, so the role of efficiency in economic growth, and feedback effects as number 3 in terms of energy rebound effects. So those 2 parts kind of go together. And those are the 3 parts that are featured strongly in the Marco modeling framework, and then close with an example where we've applied it to the UK with an electric vehicle transition question. And I should also flag up that I'm presenting here, but also that Jaime Nieto, who's also speaking here, is also one of our kind of co-contributors for this modeling framework. Okay, so time is short, so let's jump in. So firstly, our final to useful energy conversion. So what we're looking at here, for those of you who are not familiar, is we've got essentially 3 stages of energy conversion. We've got primary to final to useful energy conversion. So primary energy is the energy that we extract in its raw state, so it could be crude oil or coal or gas. Final energy effectively is the energy that you purchase. So this is petrol, diesel, natural gas for your home. This is the stuff that you actually paid money for. But there is then a further process of energy conversion, because you're not paying for the petrol. What you're actually paying for is the energy service and the movement of your car along the road. And so what we find is that in this final to useful energy conversion, we lose further energy because energy can't be completely converted into work, or certainly for internal combustion engines. So in this example, only around 20% of the fuel that goes into the car is converted into useful work or useful exergy. Exergy is a way of measuring the amount of work that can be extracted from an energy source and can be measured at primary, final, or useful energy stages. And so what we do what we've done in our network over the past 10 or so years is we've looked at many what we call energy conversion devices, whether they're cars or heating, lighting, cooling, cooking, industrial processes. And we've looked at the final energy conversion into useful work across all sectors and all countries. And what we've recently completed and we're able to utilize in our Marco model is a primary, final, useful energy and exergy database. We've published the exergy data, primary, final, useful exergy data, because we can't disclose the energy data because it conflicts with IEA licensing. But essentially, it gives us the final to useful energy conversion that we need for the Marco model in other countries across all IEA countries, covering their sectors, and into over 60 final energy products and 85 final to useful energy conversion devices, or machines as we call them. So people are welcome to access that, and if you have any questions after the event, you can contact me and I can show you the data that we have. It may be useful for you. Anyway, we're able to use that. So we've spent the kind of last 10 or so years kind of developing these sort of techniques, and what we're able to then do is to use it in our model, as we'll see later. And as I guess a bonus is that using a final to useful thermodynamic based efficiency means that we can move away from economic based energy efficiencies, which is mainly the way that the IEA and the UN and others measure changes to energy efficiency. And the way that they do that is they measure essentially the change rate in energy intensity, so energy divided by annual changes in GDP. But importantly, it means that in this case, growing efficiency doesn't necessarily mean that energy goes down. So it's a kind of a flaw in the economic-based approach to energy efficiency. You can see the example on the left that actually there's a higher claimed growth rate in efficiency of 2% in 2010 to 15. But all that means is there's a greater differential between energy and GDP. And in that example, energy was actually growing faster than it was in the latter years. So just a kind of a side point that having done that for all sectors and all countries, we can now use this metric as a measure of thermodynamic efficiency progress and check it against growth rates. Okay, Second part that's included in the modeling framework is including a productive role for energy and economic growth rather than a cost share framework. So there's two ways that we've studied this. So the first one is in our macro modeling framework, which we'll see a little bit of later on. We've built an econometric model which enables us to look historically at the role of energy in economic growth, and we've put in there final to useful efficiency as one of the variables in our model. And because it's econometric, what that enables us to do is we can go back ex post and keep efficiency the same over the previous 40 or 45 years in this case, and we can see the impact on GDP. And in this case, it means that capital investment, labor, other factors of production can still grow, but they just don't grow as quickly. And so you can see that the grey line in the constant efficiency case is about 25% lower than GDP in the baseline and in the base fit and the observed cases. So from that, we're able to kind of estimate that efficiency gains, final to useful thermodynamic efficiency gains, are actually quite a close proxy for total factor productivity, and explain about a quarter of UK economic growth. So much larger than the kind of neoclassical cost share argument, which is around 5% of total GDP. Separately, our colleagues in Lisbon also studied out a kind of a statistical aggregate production function based study of thermodynamic final to useful efficiency, and to see whether it plugged the gap of total factor productivity, and actually found as really close proxy as well, separately from our modelling framework in the UK. So both of those insights have come from our exergy economics community, and we're able now to take these in our Marco model and use it to explore future scenarios based on changes in efficiency in the future. And this is in contrast to more mainstream models, which have much weaker connections between energy and GDP. So the message modeling framework, which I was involved in a recent paper, we can see here has got a CES production function and a cost share capital constraint. So what that means is that when you constrain energy, economic growth can still feature quite strongly. And so that's why in some of the scenarios they're able to function arguably as more green growth machines. So economic growth can continue, but energy can go down, because in a CES-based production function, that's exactly what's allowed to happen. And in a paper that I worked on with Jaime at IASA and others in the modeling community, we did look at how integrated assessment models could look at degrowth, but the way that it was done was to constrain the utility function, and that meant that essentially everything shrank. So capital, labor, and energy all shrank in proportion, whereas it wasn't modeling the other way around, where it's a kind of demand-side sufficiency-based scenario where energy goes down and then economic growth will go down, because I don't think that would happen based on these equations. So it gives us an alternative way of looking at how energy constraints can impact on future economic growth scenarios. I think is limited in the way that mainstream current models can show. Okay, number 3, conscious of time, keeping going here. So the flip side to efficiency gains in economic growth is if economic growth is continuing to grow and it pulls up energy, that means we must have large rebound effects also occurring. So it's kind of like the opposite side of the coin. Everybody loves efficiency because it seems on the surface to solve lots of problems, but everybody hates rebound because it's the annoying part of the story that comes with efficiency gains. And so what we see here is essentially a plots versus 1971 of global final energy demand against global GDP, continuing a fairly kind of linear-ish line. And then we see all the SSP scenarios and IEA scenarios and other energy economy models in terms of what their future projections are for energy and economic growth. And we can see them all moving to the right. And in some cases, in probably half the cases, we see energy reducing in the future rather than growing, then that's important because that's absolute decoupling between energy and economic growth. And that's something which has never happened before. In the previous 250 years of the Industrial Revolution, we've never had a single year where economic growth has gone up and energy has gone down. So something different is happening in the modeling framework. And this is the same plot. It's just shown in terms of growth rates of energy intensity. So if you have a growth rate of energy of 2% divided by a growth rate of GDP of 3%, that's a minus 1% growth rate in energy intensity. And you can see the step change in the scenarios where suddenly they pivot to much lower forms of energy demand and consumption, And then we can see in a sense the structural break that's occurring in the models compared to what's happened in the past. And so with a team of researchers, we tried to understand why that was the case. We looked at rebound in terms of 3 channels. So we looked at direct rebound, where you buy a more fuel efficient car, but you drive it a bit further. We looked at the indirect rebound, where you can respend some of those savings that you still have on other consumption in household expenditure. And then there's a third one, which is a broader macroeconomic production-sided response to those individual consumer savings. So those 3 types of direct, indirect, and then macroeconomic rebound added together gives you total economy-wide rebound. And so we looked at, from over 30 studies that tried to estimate broad economy-wide rebound, their estimates were around 60%. So over half of the savings, or over half of the envisaged savings had gone back through rebound effects into the economy. So our take home from this was large rebound effects could well be in existence, certainly from the modeling frameworks that exist. And it goes against a little bit in terms of the mainstream idea of rebound being quite small. And is a plausible explanation for why energy and economic growth can be coupled together. We then lifted the lid, I guess, and looked into what happens in terms of the integrated assessment models. Okay, so what rebound effects are there, either through the literature or through email exchanges with the modelers, and found quite small evidence of rebound effects, certainly in terms of indirect and macroeconomic rebounds, some in terms of direct rebound effects in both the integrated assessment models and the wider global energy models such as Shell and BP and IEA. So the take home here was that there's really quite a small presence for rebound effects. So not only on one side is there not much connection between energy and the economy through things like the CES production function, but on the other side, there's very little rebound effect getting back into the model. And so this explains why we can have, with a weak elastic band between the two, we can have scenarios where energy is going down, economic growth continues to go up. And these 3 features together of efficiency, a role of economic growth, and rebound effects are now included in our Marco modeling framework, and which is our post-Keynesian model built with over 80 variables and equations, econometrically estimated since 1971 to 2020 in terms of the historical past and projected forward to 2050. And so we built it over the last 4 or 5 years. And one of the scenarios that we've tested, I'm showcasing here, is the EV transition, where we're switching, in our scenario, the whole of the UK by 2050 to electric vehicles, and seeing what happens to the economy. And this is important because we've got the final to useful efficiency in. We can introduce a step change in efficiency in the modeling parameters and see what happens in terms of macroeconomic impact. So this is a schematic of the model, thanks to Jaime for creating this one, but it shows really how final to useful thermodynamic efficiency and the role of energy services as useful XG is really at the heart of the model and feeds into other parts of the modeling framework. It's not like an energy module, an economic module, and they try to sort of interact. It's really integrated quite systematically within the model and only has the relationships that the econometric estimation will allow. So we can't force relationships to occur. The 2 essentially scenarios we had a baseline scenario where we still have internal combustion engine cars in 2050, and then we have an EV scenario where we switch the efficiency. You can see here the second column, efficiency of transport, doubles from 29% to 65% by 2050. We allow some direct rebound effects, and then we model capital investment, expenditure, and prices. And we want to see what are the changes from those 3 things: change in efficiency, from additional expenditure, and from electricity prices. And what we find is we see by far the largest gains in economic growth in the scenario where we're essentially from final to useful efficiency gains. So we see those are the green lines that we can see. They're visible gains in GDP, much larger than just from the capital investment and any multiplier effect that happens there. And that also stimulates additional employment. But with the additional GDP, we lose, well, we're penalized because we have these rebound effects that are also contained within the model. So we can see here on the left-hand side, you can probably just about make out the dark blue line is with no rebound at all. That's if we just switch to EVs. The top line is the baseline with internal combustion engine cars. And then the line in the middle, the faint line, is with when we're allowing 30% rebound, direct rebound into the transport sector, And then on the right-hand side is our total impact on total final energy. So our green line, you can see there on the right-hand side, that's our EV scenario. So we lose about, I think it's about 70% rebound overall in the economy caused by the EV transition. So we're still saving energy relative to baseline, but we're not saving as much energy as you would think due to the efficiency gains stimulating economic growth and the rebound effects. So our headlines from our analysis were that the economic investment changes in terms of GDP were much smaller than the energy system changes, which caused much larger changes on the energy economy system. And the rebound effects were very significant in terms of the role that it played, both in terms of direct rebound, but overall rebound of about 75% for our EV scenario. And just to flag up that there is other Marco modelling work that's been done. So we looked at post-Brexit energy reduction targets and the macroeconomic impacts of those. Our Portuguese friends have developed the Marco Portugal model and have looked at the productive role of efficiency on economic growth and found quite similar findings to us, that around 25–30% of economic growth can be attributed to gains in efficiency. And Jaime, myself, and a couple of other researchers are just looking at building futures and a retrofit scenarios where we're retrofitting homes with insulation, but also switching heat pumps. So again, a step change in efficiency in the building sector to understand what will be the energy and the economic responses from our Marco modelling framework. And I think that's it. I've got some references, and there's a link to our Exergy Economics network. And if you want to be involved in any of that, then please get in touch with me. So thank you very much.
Well, thank you for this presentation. It was quite a quick ride, right? A lot of input for people to digest, but we have more time, and maybe also Jaime, you will also elaborate further on it. So right now we would have time for 1 or 2 clarification questions, and remember there's ample discussion time after 5 o'clock after the 3 presentations. So any clarification needed right now? Paul, just quickly for an understanding. So you said that the Marco model has a strong link between GDP and exergy demand. So any GDP change will more or less directly drive exergy demand compared to, let's say, a mainstream integrated assessment model or the macroeconomic model in there that would have different decoupling assumptions because they use final energy, not useful energy. Is that some?
Yes, exactly. You can see here the red lines here. So efficiency gains and the supply of useful energy are 2 variables which then feed into labor demand and other factors such as profit rate here, which then feed back into capital investment. So it's when we increase efficiency, we're increasing the factors which then feed into the identity equations, either expenditure or the expenditure sided GDP identity equations.
Yeah, thanks for clarifying. And then we'll keep the broad discussion for later, and move now on to our second speaker, Carey King. Carey works at the Energy Institute of the University of Texas at Austin, and there he focuses on interdisciplinary research related on the energy systems and how they interact with economy and environment, and also how decision-making by social systems actually affects energy system and vice versa. So as an assistant director at the Energy Institute, he's a macroeconomic modeler who also has many insights to share with us. Carey, we're looking forward to your talk.
There we go. Now I'm unmuted. Thank you for having me. Does the screen look fine?
Yes, it does. Yeah.
Okay, thank you. All right. So yes, as Stefan was saying, time is short, so I will get into this. For those listening here, my background is mechanical engineering, and yes, I've been thinking about life cycle assessment and using energy and material flows into macroeconomic modeling now for the last 10 years. And so this is a culmination of what I've learned, and I'm going to discuss what I call the Harmony model or the Harmony framework, which at the moment is a toy model, and I'll talk about how I am working on calibrating this to a model for the United States. So what is the harmony model? It stands for human and resources with money model. It's built from a model that was called HANDY, which is human and nature dynamics. So I kind of just took HANDY, but put money into it at the end and to just keep a word there. But what the purpose of this modeling framework is to be the simplest framework that can do the following, which is explicitly track stocks and flows of mass, because we know that when we extract mass, this becomes a feedstock that can be embodied in machines like capital and feeds people and becomes population, becomes people fundamentally as well in terms of living beings. So food or structure and mass that becomes people. Explicitly track stocks and flows of energy, or what we call as energy. So that's like fuel to operate machines and food for people. And then to be macroeconomic or think about other social variables in the economic sense, track stocks and flows of money. So this is uses this stock and flow consistent accounting approach. As Paul mentioned, this is also based on kind of mostly a post-Keynesian approach, as well as in the concept of endogenous money, and from which I borrow the work of Steve Keen. So essentially blended the harmony model, the toy model is a blending of Steve Keen's kind of simple model of wages, labor, and endogenous money, or a bank, with a very simple model of an economy. So how does it work? I'm going to summarize kind of the structure of the harmony model, at least the toy model. And in the toy model sense, it is just one resource here that I'm just calling nature. It's like a forest, so it grows back and you can deplete it. And the economy extracts nature, and when it extracts nature, does four things with these extraction of nature, one of which is to run the machines or the capital whose job it is to extract nature. So this is like the energy sector or the natural resource sector in general. So extraction of natural resources. The second thing is that it uses nature as energy again to operate machines, or the capital that makes more machines. So I just call this the goods capital. And that's the two sectors of the toy model. That's it. A third thing that the natural resource flows have to do is to become the nature embodied in capital. So this is to say, if I build more capital, I need some of the resources become that physical machine. And there is nature left over for human consumption or household consumption. And that conceptually is something like food to survive. So there's an investment choice in the sense of an economic behavior or some assumption for how investment choices are made. This drives a goods flow from the goods sector. So this would be the new capital goods getting produced. The investment choice is made by each individual sector. There's an investment choice by the goods sector, investment choice by the extraction sector of how much more capital to invest in. And if there are the way the model closes, at least that I've published, is that if there are any output of the goods sector that is left over after investment, then this becomes consumption for the households. And the same thing for nature. If there's leftover resources extraction, then this becomes available for households. And this ends up constraining labor. If there's not enough human consumption or nature consumption left over for humans, the population will go down. So there's an endogenous population birth rate or death rate assumption. The birth rate's constant. So if you need labor to operate capital and you don't have enough nature left over for humans, then the available labor supply will go down, and that feedback is included in the model. So this is conceptually what goes on, and many people can perhaps draw a similar diagram, and then putting it into equations is a perhaps slightly different task. But in general, yes, there are economic decisions or behaviors to assume. The one in my published paper so far is essentially a decision of how to govern wages and how to make investment choices. And these end up being constrained by capital, labor, and natural resources, which is to say, if you want to invest 100 million euros and 100 million euros to become new machines needs 100,000 units of nature, but there's only 500,000 units of nature available, well, then you can't invest 100,000 euros. You got to invest less. Okay, so the structure of the harmony model, that's a little bit of it. Here it is in sort of the input-output format. So this is just kind of the standard input-output format, just to maybe look familiar to people. But I've had someone suggest that this is a useful way to say it, in the sense that what I described on the previous page is this sort of physical domain of the flows and the constraints to some degree. So the input-output table here, if you will, of my 2x2 two-industry model of goods and extraction. So the A technical coefficients are described in a physical sense. The big X's are gross outputs in a physical sense, so not in a monetary sense, and then the P's are prices. So essentially, it's a model that describes the world physically and then solves for prices on top of that. And the prices come from this sort of other domains of assumptions, or includes these other domains of social and political economy, if you will. How are wages dictated? Equations for, how would you pick an interest rate? You have an equation for investment, as well as pricing, right? So what is the assumption for how prices are formed? So effectively, the model solves costs, and in a post-Keynesian sense says that prices are some sort of constant markup on top of costs, like 10%, prices are 10% more than costs, for example. So that's kind of a quick overview of generics framework there. And now I'll go into a little bit of detail here for this audience on the idea of the input-output table. I'm just calling it a use table here. And conceptually, what I'm working on now to calibrate this to the US is to break it into these three parts. There's a part that describes the energy flows, there's a part describing the mass feedstock flows, and a part describing monetary flows that may not be, or not associated with energy or mass flows necessarily, services sectors perhaps. The toy model only has the first two, really. There's sort of no separate pure monetary sector. And then the lower left here is the 2x2 kind of input-output matrix, and I'm going to go through this just a little bit here in terms of the technical coefficients. So if we look at the energy part only, these two black highlighted, I'll put my pointer on here. These two black highlighted expressions represent the energy consumption required to operate the different types of capital. So if we look at this one, it has a factor eta E sub E for extraction sector. The other part in the denominator sort of represents the capital productivity, if you will, of extraction. So as you deplete more of the resource Y, the capital productivity essentially goes down, and you require more energy to get the next unit of resource out of it. So this term essentially represents the natural resource consumption that is required to operate the capital whose job it is to extract resources, at least per unit of extraction. So this eta is a place where you can describe as Paul was kind of referring to, the laws of thermodynamics. This eta factor cannot go to zero, right? If it's zero, then you're sort of breaking the second law of thermodynamics, that you can perform work without any energy input, or at least have no efficiency losses. So this is where that kind of idea would come in. It's describing that factor. The other one is the same thing, except for the goods sector. So the natural resource consumption required to operate capital that produces goods. So if you want to pontificate higher efficiency, then you could lower this eta G factor, and that would be like a more efficient machine. And so in the toy model, there's essentially one energy carrier. There's just one resource, and it's magically energy. It's magically physical resource that can become capital goods, and it's also food that can feed people. So it's just one, right, to be a simple toy model, but to show the principle of doing this. And there are two fuel coefficients for only two types of capital, or one type of capital in each sector. So when I think about calibrating this to the United States, I'm thinking maybe something like 17 sectors, but this is slightly up for debate, but I've kind of roughly got it configured that way, largely to tailor to the International Energy Agency data and the framework that Paul mentioned, but didn't go into detail in terms of how they summarized data from the International Energy Agency and how they describe energy use in different sectors. But we can imagine now there's a matrix of these eta characteristics. There's an energy carrier from industry I, natural gas industry, electricity industry, for example, that's needed to operate capital type K. So there's multiple types of capitals, and there's multiple industries that produce energy carriers plus other types of economic outputs, but you would need this matrix to characterize them. And the K here is the capital, for example, type K owned by industry I. So if I'm in industry, I might own a building and a factory and vehicles. And each one of those is going to take different kinds of fuel inputs to operate and be part of the energy consumption of that industry. So this is an attempt to characterize that. And the CU here is capacity utilization. So in the framework I'm using, capacity utilization can fluctuate up and down. And if there's a constraint on resources for the given amount of capital, then capacity utilization has to decrease to essentially keep the conservation of energy true. So if we put this into the framework of the toy model, it kind of looks like this on the left. You have this epsilon eta matrix, and then essentially a capital and capacity utilization matrix, and you multiply those together and you get this thing at the bottom here. So it's kind of intuitive and just very straightforward when you think about it this way, that, if I have more capital, I consume more energy. If I have more capacity utilization, I consume more energy. So those are the, there's an investment decision that dictates the capital, the state of the economy, and other behaviors essentially dictate a targeted capacity utilization, and then the etas dictate a technological description of how much energy it takes to operate each type of capital. So fundamentally, it turns into these kinds of expressions. And the task is to, calibrate that to the real world data. So the feedstock matrix looks pretty much the same, or is described pretty much the same. I have this term here, which this complicated YXG term. That becomes, this is the natural resource embodied in capital goods per unit of goods output. So if I want to build a capital good, then there's a requirement for resources required to become that capital good. So this is the embodied mass. And you can phrase that in terms of a feedstock or sort of a matrix as well. And in the US model, I'm trying to figure out the best way to phrase this, to put together information, and I'll conclude with that as a sort of open question to people. But there's, another matrix of, what's the material feedstock output from industry I needed to make the output from a given industry. And same thing here. It looks, capital times capacity utilization times some sort of resource use factor or whatever. In this case, it's just the embodied resources. So it pretty much ends up looking the same as the energy, but it conceptually has a different idea. And so that's why I've trying to keep these separate as two different matrices to add together. And then the monetary matrix, I'll just state as calibrating to the real world data and to trying to equate all mass flows in an economy, all energy flows in an economy, and all money flows in an economy. So some of the monetary flows will be left over after accounting for energy and feedstock and multiplying times prices. And so that's what the use matrix of the monetary will be. So this is, in some sense, services, business services, lawyers, consulting, all kinds of things that it's not obvious how to account for the material flow going through them. And X hat here is the same as before, the total gross output of each industry. So that's how I'm thinking about breaking this down. To just give you a little bit of insight, kind of as Paul did, into I have a blog where I have 5 insights of the Harmony toy model. And one of these is sort of the Jevons paradox, so I'll call it the backfire and not even the rebound effect, that efficiency begets more consumption. So just in the simple model here, I'm just going to pay attention to the solid lines and not the dashed lines, just for simplicity. But the black line is a sort of standard case run, if you will, that I run. And then to simulate the gray line, I decrease the eta, or that energy consumption factor that I showed you, multiplied times capital and capacity utilization. So it's like an increase in the efficiency of operating capital, the increase in the energy efficiency of operating capital. And when you do that, the resource extraction rate can increase because it becomes cheaper to be able to extract a resource. In some sense, this also means you can deplete the resource further. So the way the model is, I'm not going into the details, but the more the resource depletes, the harder in some sense it gets to extract the next bit of resource. So if you get more efficient, then this feedback is built in. More efficiency in operating a machine to extract resources enables you to lower the cost of extracting the next resource, so you can extract at a higher rate and deplete the resource. In terms of accumulating other stocks, the population goes up. I have more resources left over. for the household sectors, which means the birth rates can be, or the death rates can be lower for a while, and you can accumulate more population. And the capital accumulation of machines goes up. So if I need less energy to operate at a given level of resource depletion, there's more resource flow to become more machines. And I would say this is consistent with, of course, what we observe in the real world economy, for sure, since industrialization, more efficiency, we do have more people, we do have more machines, we do have more capital, more mass accumulation. The industrial ecology community has been, tracking this quite well in terms of stocks and flows. And this modeling framework is just 100% consistent with that. So that gives some confidence to say, well, let's calibrate this to the real world. I showed you this, it's just one resource and two sectors, two types of capital, and then model calibrated to the real world or a real world economy. The question of exactly how much detail you need. I think I'm going to have something like 7 or 8 natural resources, maybe 20 or so types of capital for the US model. And yeah, I'm targeting right now 17 economic sectors for the United States model. And this has become possible, of course, because of a lot of the work in the industrial ecology community and energy analysis community of accumulating information. So if it wasn't there, I probably wouldn't be trying it so much. But I'm blending data from the International Energy Agency, including the work essentially of Paul and his colleagues, the Exio-based database, as well as a paper that was really useful for me from Jan Streeck from the group in Vienna, the total material stocks and flows in the United States, and then just supplemented with other data from that are specific to the United States on this. And so I know some of the work going on and by Dominic Wiedenhofer and Jan Streeck and Stefan and others are, looking at coming up with standard ways to calculate material flows for different countries. And that'll be extremely useful if we want to mimic these types of economic models and duplicate them and make these models for different countries. So this just gives a hint of at least the somewhat progress I've made. I haven't put it all into the format I've indicated, but this would be an example of just tracking the natural gas flows. This is a blend of feedstocks and energy use of the different sectors. So each sector is a different color for the United States. So this is to say, this is becoming quite possible now. This is just a snapshot of looking at the flows of materials that go into homes or residential homes, trying to use information from the industrial ecology community, including end-of-life outflows, which are at the top. So inflows and outflows. I realize there's a lot of uncertainty here, but I guess for my purposes, if I can get the right order of magnitude, I feel like I'm doing well at this point. I think this is slightly better than an order of magnitude. Instead of tracking materials flowing into a specific type of capital, of course, we can track the specific material and what it turns into, or different types of capital. So this is an example of steel broken down by the different uses of becoming different types of capital or goods on the right: appliances, oil and natural gas wells, homes and commercial buildings, and these kinds of things. So this is a lot of work. And of course, the community does this and tracks this and what it becomes in terms of the stock of material that exists in capital. So this is just an example of light-duty vehicles, an estimate of the stock of materials in light-duty vehicles of the United States. And so there's a sort of questions here. I'll conclude on this slide. What are the challenges for maybe integrating models and the different research teams, people thinking about economics, energy, and material flows, and can we blend all these things together in a practical sense? How do we model or determine material coefficients, like how much material it takes to become a certain type of capital or machine? Do you want to map these as a function of time or as a function of investment or production or accumulation of stocks? What's the material it takes to make a car as a function of number of cars, for example, versus over time? In my modeling, I'll probably think about it as a function of number of cars, for example. How much would that change? Are there incompatible economic theories and frameworks? Which is to say, are there economic models in which you are just not applicable for applying conservation of energy and mass and second law of thermodynamics explicitly into them? And do they therefore not help us understand these kind of material and energy flows and feedbacks in a proper way that an ecological economic model or a biophysical model might do? An example might be cost supply curves. right? If I don't know what interest rates are, what wages are going to be in the future, how do I know what the cost of extracting a resource is? So how can I assume a cost supply curve exogenously, or what does that prevent me from understanding? And this last bullet here, I've kind of found my need here to, I'm saying this is more my need. This may be fairly standard for someone on the call. But life cycle assessment often has, materials per products, right? Here's how much material it takes to make a car. I'm in this economic model. I've got to translate this to an industry input or industry output. So I have to translate that idea. So in the toy model, this was kind of abstracted away. Or it was so simple I didn't have to think too deeply about this. And I just had a 2x2 matrix of material coefficients, this E epsilon, if you will. But in the real world, this is really maybe a function of investment I, or multiplied times investment, in terms of I'm investing in these types of things in the model, and I need this material coefficient, and there's more capital types than there are industries, so that it might be broken out into three pieces. Essentially, there's a industry that extracts raw materials, so that's the first red matrix. May have to get multiplied times industries that take raw material products and turn them into processed materials. So I'd be taking iron ore and turning it into steel, for example, or even aluminum and turning it into a car all the way. So there's a lot of internal feedback there. And then the last one, green, may be, how much processed material does it take to make a product? So I guess that's really taking aluminum into a car or steel into a car, as that would be. And then multiplied times this I times investment. So that's what I'm thinking about right now, is that maybe I need these three matrices separately described so that I can essentially track the flows, the proper flows of materials from one sector to another. And I'll stop there. And that QR code takes you to 5 insights from my toy harmony model. I showed you one on Jevons feedback paradox, but there's another ones on how wages affect the outcome, and an insight on relative decoupling and absolute decoupling and how to think about that over the last sort of 100-year time span. And I'll stop there. Thanks.
Very wonderful. Thank you so much. This was very enlightening, and also please have a look at the blog and the reports papers to check further details. Are there clarification questions at the moment? We saw there was one exchange on the chat already on Paul's presentation. That's very good, Benny. Other questions and comments for the moment? And by the way, Jan Strick, whose work you're mentioning, is also among the audience. And our colleague Dominic, he's currently traveling home from a family holiday, so he's very much looking forward to seeing watching the video recording. He can't be with us today. It's interesting that you're mentioning the LCA factor, because these are results that are easily available, right? We call them also sometimes the product environmental footprints, but of course they aggregate over all the stages that you're mentioning, right? The raw material, the processed material, and so on. And they do another major simplification, which I think we really have to disentangle for economic modeling. They ignore stocks and flows. Everything in LCA, everything is a flow. So when you produce a car, you need 10 to the minus 8 car factories, assuming that the overall production volume of a car factory will be 10 to the 8 cars. And that means you consume all materials, including the capital requirements, in the moment where the final product is consumed. So the steel in the steel mill to make the car robots, welding robots, is allocated to your car. And of course, we can't scale up these factors. We really need, as you describe it, Carey, first this disentangle. What is the material requirement of the product and the raw materials, and the same for the capital, and then have a proper stock flow dynamics in these models.
Yeah, I'd be interested in how much people have thought about that. And I have to say, being more of an energy person coming into this work, I've spent maybe 5 times more time on trying to deal with the mass stocks and flows than the energy. So it's a lot of effort. So
it's a new merger from many people, right? Also, this whole circular economy consideration, right, now coming into the energy sim models, it is a big thing, right? Because then suddenly the quality matters at the end of life, and the stock flow dynamics matters. But anyway, let's move on to Jaime Vega, the the third speaker of today's session. So Dr. Jaime Vega is affiliated with the University of Valladolid in Spain and also University of Leeds, same as Paul. And he combines his work, so to say, across both places, part-time, and his efforts focus on researching the interactions between economy and environment, and of course, especially with the exergy energy link in the industrial network. Jaime, please, the floor is yours.
Thank you. I'm gonna share my screen. Sorry. Here it is. Okay, all good?
Perfect. Yes, perfect.
Yeah, nice. So thanks again for inviting me. As you probably have already realized, I'm like a double agent in between the exergy economics people, and also now you will see that also with the system dynamics space. So today I'm going to introduce you to the MEDEAS modeling framework. Developed along with my colleagues in Valladolid, Spain, the group of energy, economy, and system dynamics. Basically, I'll walk you through the model by letting you know why did we develop this model. Then I'll show you the very model, and also some of our main results. I will combine results from different publications. And finally, we will discuss the main conclusions that we can come up with after looking at our results. So why MEDEAS? Why did we build this modeling framework? So even before I was engaged with this research group more than 10 years ago, my colleagues identified several gaps in the literature on integrated assessment models or energy economy models in general. For instance, we identify a narrow focus on energy systems in all the modeling efforts in the literature, or most of them. The disregard of supply constraints, especially from the resources point of view. Then an stylized representation of the socioeconomic dimension, and this was precisely the reason I was first hired in my research group to develop the economy module of the MEDEAS model to achieve a really integrated model where the economy is fully integrated with the biophysical dimension, differently to most of the conventional models, which tend to use the economy as an exogenous stylized representation. Then, of course, this leads to a weak socioeconomic biophysical integration. And also we identified a huge dominance of optimization models in the literature. So for that reason, we developed MEDEAS. MEDEAS is a policy simulation model, which is different to optimization model in the sense that this model doesn't optimize a result previously defined. So we just simulate policies and the results can be ones or others. It doesn't optimize. Disequilibrium is the main or the natural state of the economy relationships. It's based on system dynamics. So this methodology is particularly convenient for our purpose, an integrated process, feedback rich. We wanted to implement feedbacks between the economy and the energy systems. So it's feedback rich, as mentioned before. It considers stocks and flows because conventional economics, sometimes they disregard of stocks and flows. It can account also with tipping points, delays, things like that they're very useful to look at. It's combined within a multi-regional input-output framework with sectoral disaggregation with 35 different industries. Therefore, it's also demand-led, as in the input-output analysis framework. I don't know if you are familiar with it, with the input-output analysis. I guess that you are, but I don't have time in any case to go into the particulars. It relies on complementarity of resources instead of perfect substitutability. These bridges with Nicholas Georgescu-Wegen, for instance, in ecological economics. So it's as I said before, everything was pretty convenient for our framework. And finally, it's a post-Keynesian model with a neo-Kalekian inspiration in the background. Income distribution is what in the end determines the final demand. Investment is key in this model, and investment is determined in turn by profit expectations by employers or by firms. And finally, it accounts with supply side constraints. For instance, linking with the post-Keynesian tradition, labor force is one of the constraints, and we add to that the energy constraints. So in a nutshell, without going into a lot of particulars, because we don't have time, it's an integrated model. It's fully integrated in the sense that all dimensions, or at least most of the dimensions, are not separate from each other, and the causality links goes multidirectionally. In conventional models, normally the economy affects the environment, the economy affects the energy demand, but there's not normally a feedback into the economy system. So, as I said, in a nutshell, the economy module let us determine final energy demand, and with the energy module, we estimate energy supply. We compare by 5 different final energy sources. The energy module tries to take primary energy resources and transform them into the final energy sources that have been demanded in the economy module. For that, the model, it needs energy infrastructures to be unfolded, and in turn, that requires minerals and materials. Then, final energy demand also generates CO2 emissions, and that can feed back to the economy through climate change damages. For the sake of simplicity, so far, we always have this disabled, because it introduces a lot of uncertainty. So all the results must be taken as conservative assumptions. We can also estimate the land use for renewables and the water demand. But the key is here, because energy demand, if the comparison between energy demand, primary to final energy demand, and energy availability is what is constraining the economic system. And how is that done? Again, without losing a lot of time with the particulars, we have sectoral final demand. It's estimated econometrically with parameters of historically determined parameters for household consumption and gross fixed capital formation. That depends on the primary income share and the labor and capital compensation expectations that employers and employees have. These expectations are determined by exogenously in the scenarios and by population growth as well. And with this sectoral final demand, that enters into the input-output analysis system. And with that, we estimate the required sectoral production, accounting for all the backward and forward linkages between sectors. Then with energy and labor intensities, we can estimate final energy demand and labor demand. As said before, in the energy module and in the employment submodule, we can estimate energy availability, energy supply by different sources, and employment labor supply as well, also disaggregated by 3 different skill levels. So then we check whether supply meets demand, and if supply is lower than demand, then expectations are nuanced. It's not that there is an economic collapse whenever there is a shortage of energy or there is a shortage of labor. The thing is that if you were expecting to grow by 3%, then maybe that year you are growing 2%. And if that situation persists in time, then it may eventually lead to an economic breakdown. So as a result of this modeling framework, we have been able to publish different papers. Some of them are related to my PhD thesis, applied to the European Union, applied to the global economy, to the world economy. We also have a more general, because the previous 2 are more focused on the economy side, because I'm an economist. This one explains the model in general, going module by module, and runs a couple of scenarios. And also recently, a collaboration with a cross collaboration with the University of Leeds, with Manuel Aramendia. Particularly, we are looking with Medeas Spain at their material requirements, but this is a work in progress right now. So very quickly, this is the typical scenarios framework that we tend to use with different points of view. I don't want to go one by one, just take into consideration that the business as usual scenario is a no policies scenario, so it keeps current trends. Then the green growth scenario is a scenario where we apply an energy transition. Installed capacity of renewable energies is increased, efficiency goes up, and it is supposed to increase the expectations of growth. And finally, the post-growth scenario is a scenario where we apply also an energy transition, but we apply also an important socioeconomic transition as well. It's not only technological, it includes technological developments, but also important socioeconomic dials, like we reduce demand, we take labor productivity slightly lower, income distribution is oriented towards labor instead of capital, then efficiency goes high as well as in the green growth scenario, but it goes even further because it includes demand-side efficiency. And we also, this is very important, we apply a different economic structure, a different industry sectoral breakdown that is targeted, is policy oriented. So we apply industrial policy. We can go into the particulars later. So some results that we can see with this modeling framework, looking at the European Union, for instance, this is GDP, employment, and CO2 emissions. So for instance, with the business as usual scenario, what we see is that GDP very quickly goes down because if there is no energy system transformation, then there is a shortage of the availability of non-renewable energy sources. So GDP can't grow as much as it expected, and in the end, it leads to economic breakdown. And emissions, they go up at first because we keep consuming fossil fuels, but then because of the economic breakdown, emissions go down as well. Green growth, in the green growth scenario, we see that we can keep certain level of economic growth, actually even higher than in the current trends. But then at some point, right in the middle of the 30s, it could face a stagnation because of the energy trap, because of other considerations, because rebound effect makes non-renewable energy sources to go up as well, because you have to build all the infrastructures to the increased demand of energy, and so on and so forth. And finally, the post-growth scenario, the decline in GDP is more smooth than in the business as usual scenario, and is planned, it should be planned, it shouldn't be a breakdown. And then it struggles to keep employment only when a working time reduction policy is applied, would be this red solid line. And CO2 emissions is it goes down the most. We can see that the green growth scenario is able to reduce emissions, but not as much, because of this increased demand. This increased demand, it makes that non-renewable and fossil fuels demand keeps at a high pace during this time. We can see that as well. This is emissions for the world level. Look at, for instance, the business as usual scenario. This is 2050, the dotted lines. So we can see that in the business as usual scenario, emissions in the world to the world level, if we do not take into consideration energy limits, here what we do is that we switch off the energy resources limit. So if we consider that there are no energy limits, then emissions are going up. If we consider that there are limits, emissions are going to be lower, but there will be economic breakdown. In the green growth scenario, if we disregard energy limits, then we are not going to achieve the GHG emission reductions limits goals, because actually they are going to increase by 2050. If we consider these limits, then we obtain a reduction. But this difference between this and this, it has to do with constraints in energy resources availability. It doesn't have to do with policies. It has to do with constraints in access to different fossil fuels. And it's only the post-growth scenario, the only that is able to reduce in any case, regardless of energy limits or not, is able to reduce GHG emissions. Very quickly, this is, as I said, it's a work in progress. Materials used for Spain. We can see this would be kind of a green growth scenario, and this one, the sufficiency scenario, could represent the post-growth scenario in the previous slides. So here we can see that for critical raw materials, the green growth scenario would also put a lot of stress into the system by an increased level of demand for chromium, copper, silver, tin, that could be avoided in a sufficiency scenario or a post-growth scenario. See that the orange one is the rest of the economy, so it doesn't have to do with entirely with the energy transition. And the same could be applied even more intensely to cobalt, graphite, lithium, nickel. So overall, the conclusions is that energy availability is key for understanding the transition and the growth dynamics. That no policies or business as usual may lead to economic and environmental collapse. Green growth for us is like kicking the can down the road. It's like avoiding the problem now, but pushing it to the future. So if we do not apply socioeconomic transformation along with this technological change and keeping the huge economic growth without socioeconomic transformation, then the problem is going to be moved forward. We can face energy constraints as well, and we are probably not getting to the climate change goals as well. Finally, the post-growth scenario shows that there are post-growth avenues to socially sustainable low-carbon transitions. But of course, the key challenges is meeting social needs without growth. This is not a straightforward issue, of course. materials demand and also land could be is not something negligible as we've seen before. And also, of course, we have to look at north-south just transition, because we have looked at the European Union and also as the world as a whole, but we have still to investigate into the north-south relationships that could be also key into these transformations, especially looking at China. In this sense, the William model, it's a different model compared to Medea's, especially if we look at the economy module. It's a different model, but it's based somehow in Medea's for some of the modules, for instance, land or the energy system as well. And in that one is disaggregated by more regions, 35 regions. Sectoral disaggregation has been improved as well. So this is work in progress again. So this is all from my end, and I'm open to your questions. Thank you.
Jaime, thank you so much. This was really insightful, and also the results really interesting and detailed. We have directly a few follow-up questions, and then we have 15 more minutes towards the end of the seminar for a general discussion. For the Q&A, there is first a question directly from Tommaso. How do you define the energy limits in your model or scenarios?
Do you mean how do we determine if there is a 1% reduction shortage, sorry, in liquids, for instance, in oil products?
I think so, yeah.
Yeah. So we made a simplification. So the first simplification, because it's input-output analysis, a complementarity implies that it's not perfectly substitutable, and then the most constraining shortage is the one that determines. So, for instance, if we have a 2% constraint in one sector for liquids and a 3% restriction for coal, then the 3% restriction is the one that dominates. And also, if it's a 3% restriction, then we reduce that sector's output by 3%. It's a simplification. We have been working for this Medea's Spain and also for William in improving or refining, polishing this, for instance, applying it like sectorally. One sector, it depends more on coal than on electricity. Then if it's coal, what is in shortage, then it's going to affect you more than if electricity. And if you go towards electricity point of view, then electricity will be the most constraining one.
So in short, if I got you right, so you simulate a phase out of fossil fuels due to climate policy by reducing their availability exogenously.
Sorry, come again?
Because you said you have this reduction rate, 3% per year and so on. And I think in your model overview, you show that you reduce, or that energy availability is an input to your model. Doesn't mean you simply reduce the availability of fossil fuels in your scenarios.
No, yeah, now I get it, sorry. So it is based on Hubbard curves. So it's geologically determined. With the best guess in the literature, we use the works of Moore and others for all non-renewable primary resources, not only oil, also coal, also uranium. So we use geological constraint, Hubbard curves, and we use the best guess in the literature.
Okay, yeah, that makes sense. Thank you.
Yeah, I'll just comment on how I plan on trying it maybe a little different. It's just to define the resource itself, give it a size and how much capital it takes to extract the next bit. And so the investment in case of oil would be to drill. The ability to drill would be how many drilling rigs you have. And then there would be a decline curve of each of the cumulative oil wells drilled in all of history. So that's what I'm thinking now instead of a Hubbard curve. So the production would there be a function of drilling, not where the Hubbard curve, I'm not sure. I guess there's no explicit drilling to say how much it is. You just kind of assume the drilling happens to produce a particular Hubbard curve scenario. So that's kind of my method is kind of, I don't know, I'll call it brute force, but it may be so detailed that it gets overwhelming. So that'll be the trade-off maybe.
Yeah.
I mean, there has been a major paradigm shift, right? Especially in fossil fuel availability from a fear of constraint peak, everything oil and so on, to an actual oversupply, right? I mean, the supply cost curve say there's at current prices more than enough. We should keep it in the ground. I thought that the availability of fossil fuels is the more price or policy constraint rather than actually a question of availability. Like
For that reason, what we do is that our model is flexible enough so we can switch off the constraint. So okay, if you think whoever, I mean, if someone doesn't want to trust the literature on geological limits, that's fine. Then you can switch it off. And if you switch it off, then you will realize that the problem is going to come up from climate change. So
yes,
that's the trade-off.
yeah, and that means you could also use these curves maybe to simulate a fossil fuel phase out. Then
exactly, yeah. Actually, in the European application, what we do, the main restriction is not geological; it's policies. So the restriction is applied by the policy of the European Union. So the European Union has committed to reduce fossil fuels by this amount. So there is an estimate of the reduction. So what we estimate is, okay, you want to reduce that. We're going to keep that for granted. If you want to keep that for granted, then what is going to happen to economic growth? If you want to reduce that, efficiency must go up by a huge degree that it's thermodynamically impossible.
And there is a direct.
So that
Please,
as I say, that policy, let's just say fossil fuel phase out would be translated to forcing less investment in drilling or less need for drilling rigs or a lower capacity utilization for existing oil and gas wells, for example. That would be translated to those kinds of variables.
Exactly. This is also a possible way. So we have a direct follow-up question from Tommaso that I'm going to read. Then I'll give the word to Umet, who raised his hand in the chat. And then we have two questions in the chat by Benny that I'll try, maybe have to repost, but let's start with Tommaso. So when we have now this change in fossil fuel availability, he's then asking, where does the environmental collapse come from in your model? Is it the climate feedback on the economy, or if it doesn't exist, or is it the resource constraints? So where is the collapse coming from?
Mostly the environmental is via the land use restrictions, also mineral restrictions, but these are not feedbacked in these representations. We are doing that now. Also via climate change, although Tommaso says, and it's true that it's disabled, but if we enable it, the thing is that the uncertainty is huge. But what we know is that environmental collapse is coming from the 60% increase in GHG emissions. So that's what is letting you know. It's not affecting the economy because it's disabled, the impacts of climate change, but then you have the resources availability one.
Exactly. And of course, we know from other analysis that this amount of emissions will create severe damage to
the
economy. Right. And now, Umit Timosho, you can unmute yourself. Yes, you are. Hello.
Yes. Good afternoon. Thank you for very interesting presentations. So I'm from GRC, European Commission. So regarding this latest presentation, I don't know, my video does not show up, but I'm joining through browser. Do you hear me well?
Yes.
Perfect. Okay, so regarding this, the last presentation, I was wondering, so how do you exactly model the energy constraint. So suppose that you find out energy supply is in shortage, then I assume you are not using price-related reaction, since you have indicated that you use kind of post-Keynesian philosophy. So do you have some kind of stock-to-flow targets, or you say also input-output model? And do you have some kind of quantity adjustment mechanism? I think this is really important. So I would be interested to know these details if possible. Thank you.
Yes, basically, so, we use an input-output framework. So that's what allows us to determine final energy demand by 5 different energy sources. That's an input to the energy module. Then the energy module knows that the economy wants this quantity of electricity, this quantity of liquids. So it takes primary energy resources. Then these primary energy resources are coming from geological Hubbard curves. So the more you extract, the less resources that are available at some point. That might be a restriction to the economy. And as I said before, that can be switched off in case you think that this is a restriction, a very tight restriction. That's how it works, basically. Yes.
But within the economic model, how do you exactly model this shortage? So you have like with an input-output framework, or I don't know, you might have some consumption reaction.
It's the input-output framework. So you have all the production by sectors, by 35 sectors. So say that sector 3, sector of food, was producing $100 million of economic output, and there is a shortage. There is a shortage of 3% in oil. So instead of producing $100, it's producing $97. So all the analysis comes back with this new production, with the feasible production, and the energy intensity and the labor intensity, the feasible employment and the feasible energy consumption is estimated. Of course, if there is a shortage, the final consumption equals the final energy supply.
Okay. Well, yeah. Thank you. I will have to check the details further, but thanks.
Yeah, thank you, Umit. This is a general thing, right? The models are, even though sometimes very aggregated, still very complex in terms of the assumptions. So definitely one has to engage more deeply with all the assumptions and the mechanisms as well. Paul, if that's okay, I wanted to repeat the question that Bini posed in the chat, and I'm not sure whether everybody could see that, so I will repost it again to everybody. It's about the electric vehicle study, right? The question is, if you do these sectoral improvements on individual technologies like electric vehicles, how does all this add up to a full energy demand, exergy, final and primary energy demand scenario?
Yeah, thanks, Stefan. So I think, in the reply that I posted, didn't quite make it back on the chat. So obviously we have a national model and we have various sectors. We have transport, industry, commercial, public services, residential. And so what we need to do is, with our 80+ variables, we have to work out which ones are going to be affected by this particular scenario. So for our EV scenario, we know we have a transport sector, so we can change the final to useful efficiency in that whole sector. But if it was only part of the sector, if we still had some transport sector that was not affected, we would kind of proportionally change the efficiency, so that we're effectively doing off-model calculations to then work out what are the changes to overall capital investment or household investment in terms of spending on cars, and then we put those changes effectively into the model.
So there would be some exogenous assumption on modal split, or sorry, the sectors, the technology split on electric vehicles at a cost, so you could pre-process. Yeah.
Exactly, and some assumption about that energy service. So we're particularly interested in that useful stage exergy, which is effectively our energy proxy for energy services, and then we model what those future projections are in terms of energy services through useful exergy, and then through the off-model stuff, we then work out, okay, so what is the kind of the share of cars versus buses versus transport, and how much final energy is effectively going to be used to deliver that useful stage exergy. And then we can put those exogenously into the model, allow rebound we have a rebound switch, which means we can allow direct rebound into the model if we so desire. If it's an avoid shift improve scenario, we might constrain rebound so that we, through carbon pricing or whatever, that we're not allowing rebound to get back into the modeling framework.
So you would kind of enforce that there is enough avoiding strategies because of the lack of rebounds effect that just make these reductions happen.
Yes, exactly. And then we would effectively see what the impact would be then on the constrained spend in terms of reduction to GDP, because energy and the economy are tracking closely together.
Okay, thank you. Benny, you had a few more questions directly to Jaime. Since we're running out of time, I would like to ask you to take this up with him directly. And I would instead rather take up the question posted by Aljosa. And Aljosa, the question is whether you want to speak up and then ask the question. I think it's a nice closing question that you're posing on the GDP reduction.
Yes, sure. Thank you, Stefan. Yeah, I would like to ask maybe Jaime, but also Paul. So in your model, you basically assume that there's that the GDP and energy cannot be really fully decoupled. How about like if we conceive economy not in terms of GDP, but in terms of economic activity, in terms of how much services are provided to the society? Do you think like we could have actually an aggregate growth, big growth of energy services with much less energy? And how would that change maybe like the framings of your conclusions that may have shocked some of the participants, in particular the European Commissioner representative, because they see like a complete collapse of the economy. But if we look in from the point of view of actual energy services, you may have different conclusions, I believe. I hope that was clear. Thank you.
Yeah. Should I start, Paul?
Yes, go.
So thanks, Aljosa. Yeah, that's a key question actually. Whenever we talk about especially the post-growth scenarios, because that's very important. Of course, we can do that. We have modeled bottom up some sectors like transport. For instance, for transport, you can have the same amount of passengers per kilometer with less GDP or with more GDP, or with the same GDP. Also for buildings, we are doing that for William. But whenever I want to look at energy services, I honestly go with Paul. I change my hat and I go to the University of Leeds and use the macro-UK model. So finally, and then I'll give the floor to Paul about resource constraints. Please take into consideration that maybe these days it looks like that's not the real problem, because the United States is producing tons and tons and tons of oil. But remember, just a few years ago, supply chains, the COVID crisis, the war in Ukraine, if the transition from the Russian gas to other sources wouldn't have been smooth, that would have implied, and China also changed their prospections of GDP growth because of energy shortages. So the thing is that, okay, you have that in the model and you can apply it at your will, representing whatever can constrain resources availability, whether it's a policy, geological constraints, supply chains, a war. So that's it, Paul.
Yeah, I guess The EV stuff that we've done, or the scenarios that we've run in the macro model, it kind of spins both ways, and it kind of relates back to that kind of that annoying, the second half of the coin on rebound effects. How well you can control and constrain the rebound effects. If you can't control them and they carry on as they have done in the past, big efficiency step changes that we're going to see with heat pumps and with switches to electric vehicles could then see a step change to efficiency and efficiency gains in the economy, which would spur economic growth and pull energy higher, as we saw in some scenarios. And that's what the policymakers would be quite happy with in terms of stimulating economic growth. But the penalty is pulling up energy depending on how you can control rebound. If you can't control it well enough, then some of that rebound, some of that energy saving is going back into the economy. And that means simply in climate change terms, then renewables are going to have to work harder and faster than we currently think. And the carbon sequestration technologies will have to be stepped up and also deployed faster.
Yeah, and I'll just comment, I guess, a lot of the work from the Exergy economics group that Paul and I and Jaime and Pauliuk and some of you are part of this. I've looked a lot at the scaling of primary energy to GDP. A lot of people have, but because of the industrial ecology community, you can look at primary energy and scaled, or how it scales with mass, and mass accumulation seems to scale 1-to-1 with GDP. And after the 70s, you have this, relative decoupling of primary energy and GDP. But over the 100 years, the studies that have been so far seem to show that, useful exergy still scales fairly closely 1-to-1 with GDP, and useful exergy isn't exactly energy services, but it's maybe the closest quantifiable metric that we have that has some sort of rigor behind it. So this is a good question, and one of the ideas for services that I've been thinking about is the difference between, I guess, the productive parts of the economy versus, I don't know, the purely consumptive, like households. What the scaling of primary energy going up slower than GDP or mass means is that each end unit of infrastructure will consume less energy if you accumulate more infrastructure. So in the biological sense too, if you accumulate more mass, the next unit of mass will consume less energy than the previous units of mass. Whether that means you get more services or not, that's a separate question, but you could just decrease services and by consuming less energy, or you could be getting more efficient to consume less energy and keep the same level of services. And that's, I think, a challenge to understand, but a good question.
Thank you. I think this rounds it up nicely, right? We have addressed big questions today, and I see there's two things that I would like to conclude. First is in a post-growth world, we need to be more careful in what mechanisms we depict in our scenario models. If everything grows, we can ignore these stock flow things, ignore the waste, everything. There will be more of everything that fixes it. But now we need to be more accurate, more consistent, because we can't expect on growth to solve everything. And what we've seen today is really a nice showcasing into model developments here. It is hard to understand, so everybody is invited to continue the academic debate, to look up into the details of the models, the consistency measures taken, the assumptions, maybe the new synergies with coupling models or changing assumptions. So this is really an important avenue. And the second one is this link we discussed now also at the end, that we know we have to address also exergy as a proxy for useful service. But there's more links to come, right? A link between exergy and well-being, the amount of services, the cultural context that we need for well-being, and also the question of what are good service measures. From industrial ecology, we know, and we know it from our everyday life, that the size of the products matter, right? I can drive a large car, very exergy efficient. I could drive a smaller car as well. Same with houses and so on. And this drastically, of course, scales the exergy and final energy demand. So that's another avenue of research, right? For me, post-growth economics also means getting rid of GDP as a proxy for everything, but actually opening up the box of exergy, of services, and also of well-being in different contexts. So that links us back to the topic also of the edits project, right? That also tries to add there. I want to thank our three speakers for being so responsive to our request to join the seminar. Thank you for presenting your work. Thank you also for allowing us to record this session so that the colleagues who cannot make it today or who want to look it up later will be able to do this via CMCC's video channel. And thank you also for Benny especially and Yasa for facilitating, and a big thanks to Sophia from CMCC, the Mediterranean Center for Climate Change Research, for actually facilitating and hosting this webinar today. And that's all from my side. If our speakers, if you want to have a few closing words, please do so. I wish everybody a good afternoon, a good day.
No, thank you for having me. Thank you.
Yeah,
Thanks,
thanks for
Carey.
the invitation. Nice to see everybody.
Thank
Thanks
you,
a lot
Paul.
for inviting me. Yeah,
Thanks,
thanks.
Jaime. And everybody, bye-bye.
Bye.
Bye for now.